All right. Thank you, Mohan. That was, first of all, an impressive introduction that you did from memory. I'm not sure I know my biography that well. Just two quick things on the introduction. I am one of 8 children. 6 of us graduated from the University of Notre Dame. And then one of my sisters graduated from the all-women's college across the street called St. Mary's College. So yes, we have deep ties to the university. The other thing is that Mohan mentioned we've known each other for a long time. He also mentioned the Air Force Young Investigator Award that I won. The reason I know Mohan is that he won the award the year before I did, and I didn't win it. And I noticed he won it. I literally cold emailed him and said, hey, could I talk to you about how you won the award? And of course, Mohan, being extremely generous, said, sure. This is like 2010 or something like that. Said, sure. We had a very pleasant conversation, and I won it the next year. Then we just completely randomly were both invited speakers at a conference in Germany where they had to invite like 4 or 5 international speakers. And we met up there, and then we've been collaborating basically ever since. So it's been very serendipitous, a wonderful professional and personal relationship with Mohan. And I'm very excited to be here today to talk about electrifying the future. So how do we take processes right now that are mostly thermal processes and turn them into processes that can be driven with electricity, preferably renewable electricities? And so this was working. Let me see if I dislodge and relodge. There we go. Okay. So just very briefly, I am from the Department of Aerospace and Mechanical Engineering at the University of Notre Dame. We're a department of about 40 faculty or so, about 500 undergraduates and roughly 175 PhD students. We also house our bioengineering program and PhD. So if any of you are interested in transitioning into mechanical, aerospace, or bioengineering, feel free to give me a call. I'd be happy to talk to you about it. Somehow, I have a pipeline of UIUC grads in my research group right now. I have 3 students, 2 with bachelor's degrees, including one from this department, Daniel Martin, one from chemical engineering here at UIUC, and then a 3rd student got his master's here at UIUC. So I'm always happy to accept an Illini. That's plural? What's a single Illini? Illini to my department. So I work in the general area of thermal fluid transport. I know in the nuclear sciences, you guys look at things like fluid dynamics and heat transfer. The same thing with me. I'm going to use this screen over here as my go-to screen, just in case you're looking for the laser pointer. And so I do some work in microfluidics and thermal transport, heat transfer. But then my main area is non-thermal plasmas and gas discharges. And I do a mix of theory, simulations, experiments, and technology development. And I'm very collaborative, and you're going to see that today. Everything I do is collaborative at this point in my career, and you're going to see a little bit of each of these first 3 things in the work today. What I like to say is I'm curious, so I ask questions, and then I figure out the tools I need to answer the questions. Rather than saying, I have a tool, what's a question I can answer it? So I don't start with the answer, I start with the question. You guys probably all know what a plasma is, but just to sort of baseline everyone, a plasma, right, is an ionized gas. So it's got free electrons and free ions. We distinguish in the plasma community between equilibrium or thermal plasmas, which are pretty typically 100% ionized. So every particle in the gas phase has been charged to a positive ion and a negative electron. Everything, all the particles are in equilibrium. They're extremely hot. Fusion is obviously an example, but the sun, lightning, those are great examples of thermal plasmas. Non-thermal or non-equilibrium plasmas are typically very weakly ionized. The plasmas we work with are on the order of 1,000th of a % ionized, right? So We're not talking 1% or 100th of a percent, 1,000th of a percent ionized. And so what that means is that the majority of the plasma is still in a neutral state. And therefore, you have very few electrons. They are being accelerated by the electric field. They stay hot. They're on the order of a couple of EV or a 10,000 Kelvin or so. But the ions and the neutrals collisionally cool each other and stay relatively cool to the point that you can actually touch them, right? So you can touch these plasmas with your fingers. Great example of plasma inside this room are the fluorescent lights in the ceiling. Those are low temperature non-thermal plasmas. They're neon screens. They're in plasma televisions or neon lights plasma televisions. Why we like these non-equilibrium plasmas just goes down to the basics of the collisional environment. To create, so you start with an electron and you apply an electric field, usually a high voltage, to your gas. That electron will be accelerated. It will collide with a neutral molecule. Grossly, very broadly, it can do one of three things. One, it can bounce off, completely elastic, so it just bounces off. And so you got an electron in a neutral molecule. Number two is it can excite that neutral molecule. It can put into a higher energetic state, whether an electronic state, a vibrational or rotational state. Number three can ionize, and that creates a second free electron. And typically, plasma engineers are like, that's all I care about. I care about the ionization. I want to create charge. But the reality is, it's these excited reactions that actually are the most interesting. And so if we just consider air, dry air, oxygen, and nitrogen, when you have free electrons in your plasma, they will be accelerated. They'll hit oxygen. They'll either dissociate it, which is an excitation reaction to the state where the excitation overcomes the bond, or they'll excite it into an excited state, which we denote by a star. They'll do the same with nitrogen. And then no longer electrons being involved, all this other chemistry happens, producing ozone, producing NOx, producing N2O, all of these other species that can then do useful chemistry for you. So just starting with the electron, you get all the other species. So what do I mean by an excited state? Consider nitrogen. Look, you have all these energy levels, vibrational, rotational, and what I'm showing here is electronic. Embedded, of course, in these are your rotational and vibrational energy levels. So there's all these different energy states, and when you're in those excited states, you're more likely to react. And so you think of all the things that are produced in America by chemistry. The question is, can we do it chemically with a plasma? And it turns out you can. I always like to say plasmas are unsung heroes. When I go home and I tell my parents I work on plasma, they think I work on blood, right? Because that's what they know. If you Google plasma right now, you're probably going to get the opportunity to donate your plasma and make some money, right? That's what most people think of. But they're actually these really important, obviously, technologies in this room, but also very useful. And so people have started to harness the chemistry of these to do things like dentistry, clean your teeth, to heal wounds on the skin, or to disinfect a surface, or even to promote biological growth in agriculture, right? And so these are all examples of using the useful chemistry to do something with these low temperature non-thermal plasmas. My group has done a lot of work in this space. Mohan actually summarized this slide for me, so I'm not going to go over it. I'm going to just talk about two areas today in catalysis and electrochemistry and tell you basically a story about each of them. But the big picture here is, can we electrify the chemical goods production process? Almost all goods are produced from some sort of fossil fuel. So you're going to take natural gas, you're going to take oil, and then you're going to do some refineries on some refinery processing on it. And then with that refined process, you get other chemicals that then are the building blocks for medicines, for fuels, for chemical cleaners, for plastics, for fertilizers, whatever it may be. That's typically a thermal process. So that's producing a lot of carbon dioxide. If you look at how we get a lot of natural gas through, say, fracking, we can't capture it all, and we don't want to dump it in the atmosphere. So we just light it on fire and burn it right on spot. It's called flaring. In fact, there's a highway relatively close to my house that there's an eternal flame that just burns constantly, right? And so that both of those produce a lot of CO2. That's no good. That's a pollutant, right? And any of the energy needed to heat, right, is usually coming from a fossil fuel as well. All of this is not good news. So the question is, could we replace that processing or any steps in that processing with the plasma running off renewable energy? You could do it in a distributed manner if you needed to, and therefore address that. Or if you take something like fracking at point of sight, maybe you can actually react the natural gas and make it into useful chemicals instead of just burning it, right? So you could even skip the middleman. Are there things we could do on site, or we could do in centralized plants? And I'm not the first person to think about this. Lots of other people have thought about this. Here's two examples that you can find in review articles that think through how can we use electrically driven processes, in my world, plasmas, and other people's worlds, electrochemistry, to do this type of work. And I'll give three use cases that we kind of look at in my research that I'll show today. One is ammonia synthesis. Right now, you would take nitrogen and hydrogen, go through what's called the Haber-Bosch process to produce ammonia, NH3. And it turns out that ammonia is one of the most important chemicals out there today. If you were to ask someone, what are some of the most important discoveries of the 20th century, they would say the following: flight, computers, space travel, Haber-Bosch. You're like, why Haber-Bosch? It's because fertilization has fueled the growth in population across the globe. Without fertilization to do mass-produced produce, we would not be able to not only sustain produce for our people, but then the produce that goes into all the meat industries that also sustain our people. And so this is a huge industry. And the question is, can we do this more efficiently with the plasma or a plasma process? Can we do it electrically rather than this Haber-Bosch process? Another use case is the flaring that I talked about. And I said, what if we could react that natural gas right on site? What would we react it with? Well, air's pretty abundant. Maybe we could react it with nitrogen or oxygen and create some useful products, or even with CO2. Can you react natural gas and CO2, form what's called syngas, which are then can be very useful to produce downstream products. A third one is, could we just do CO2 recycling directly? If we could capture that CO2 or react it in place, could we make something useful with it? For example, formate, which is a useful chemical product. So these are three use cases that I'll be talking about in my two stories today about liquid phase goods production through something we call plasma electrochemistry, and gas phase goods production through something we call plasma catalysis. So starting with the first one. The cool thing about these low temperature plasmas is that you can bring them in contact with sensitive substrates. That includes your finger or a strawberry, but also liquids. They're low enough temperature that they don't evaporate the liquid right away. And so you can do this in a variety of ways. You can put it inside the liquid, as I show here. You could put it remotely and just bring the plasma down to touch it through a plasma jet. Or you could actually have the liquid act as a resistive element in a circuit, a high voltage circuit that drives the plasma. And now the plasma is touching the liquid. And what is interesting about that is that you actually need charge transfer across the plasma liquid interface to sustain the circuit. This is an analog of electrochemistry that's been actually used widely. It can be used for material synthesis. It can be used for analytical chemistry, wastewater purification, and catalyst-free chemical synthesis. And I'm going to talk a little bit about some of these applications in a bit. But the analog to this is essentially an electrolytic cell. Some of you might remember freshman chemistry. You would put two electrodes inside water, for example. You apply high enough voltage, you get a current that goes. You split water, you get hydrogen and oxygen. Okay. So the question we ask is, what happens if we change one of these electrodes with a plasma And if we make it a plasma anode, that means that the electron circuit somehow has to get out to complete the circuit. And so there's an oxidative process here. And if we make it a plasma cathode, that means that electrons must be entering the solution from the plasma phase, and there must be a reductive process at that electrode. And so just to show you that this is a pretty cool phenomenon, what I'm showing here is a plasma in contact with the solution with the pH dye. The pH dye is nominally orange for being neutral, and almost instantaneously filling up the majority of this reactor vessel, you see it's changing it to green, and that makes it basic. And so you're doing some chemistry instantaneously, low temperature, low power to create this basic environment. And what is that process? Well, in this configuration, we have a plasma cathode. So it's injecting electrons into the solution. And just like you have free electrons in the gas phase, in a polar solution like water, you can have free electrons. We call this hydrated or solvated electrons. And what happens is the water likes to be polarized by them. They form a little bit of a shell, what we call a cavity, that creates essentially a 1s orbital. So you have a stable electron. Those electrons are very reactive. They like to react with basically anything, including with water to electrolyze water. And so we've been asking ourselves many questions about how these processes work. That electron gets in, it goes through a reduction process, or it reacts with water through second-order recombination. What can we do with that? What kind of chemistry can we drive? At the interface of the plasma liquid, you'll get a bit of water vapor, and that creates a bunch of reactive species as that water gets excited and associated by the plasma, and that can then diffuse in and also create a bunch of reactive processes. So we ask ourselves what's happening there. If we switch this so the electrons have to get out, we have a whole new set of questions. How do electrons get out? Do you form solvated electrons? What's the mechanism? What is the process? If you recall your fundamental plasma physics, what is the secondary emission coefficient of this? I'm only going to talk about the first configuration today and show you a series of papers at a very, very high level. So I'm not going to go into detail, that combine experiments, theory, and simulations to try to unravel some of these questions. And so the first question we had was, are there really solvated electrons in these systems? Is this a real thing? It makes sense on paper, makes sense on a slide, but is it a real thing? I told you these solvated electrons form essentially a 1s orbital. That means you can excite them into the equivalent of a 2p orbital, and all it takes is light that's around 700 nanometers. So a red laser pointer, literally this, what I'm shining at the screen, is able to do that. And so if you were to shine a red laser at the plasma liquid interface, if there's solvated electrons, they'll absorb the light. And if it reflects off the surface, you'll measure less light than what was incident on that surface. We call this total internal reflection absorption spectroscopy. What I'm showing you is an absorption spectrum for different wavelengths, both theoretical, which is the black, and our measured data, which is the red, and it's pretty good. We confirm this in another way where we can predict the relationship between the intensity of the signal and how much current density we had. So how much current and how wide the plasma was. Was it a large spot or a small spot? And so we could relate the current density, the absorption on a log scale, to the current density, which is J on the X axis. And we see we got two different trends. We got one where it's a linear relationship and one where it's a cubic relationship, right? On a log scale, a power law of 1/3. And we could develop theories that would predict that based on the fact that as those electrons come in, they want to react with water in the second order recombination. And it all depends on how long we allow them to do that. And if we can pulse the plasma faster than they want to react, we get one relationship. And if it's slower, then we get a second behavior. All right. So that answered the first question. Could we measure these solvated electrons? Another question is, what can they do? And so I'm going to actually show not my work, but Professor Sankaran's work here, where he shows that they can reduce, for example, metal cations in solution. So now you take a silver ion in solution, you react it, you get neutral silver. What happens? That silver wants to gather together. You get nanoparticles in a colloid in the solution with no other chemicals. You just throw in some silver salt and you hit it with the plasma and you get this beautiful colloid solution. Another example, this goes to the use case of carbon dioxide. You take fizzy water, you take your LaCroix, right, which has got carbon dioxide in it. You hit it with the plasma, you reduce the carbon dioxide to form a radical anion. That then can combine with a proton to form formate, or it can recombine with itself to form oxalate. And again, you can imagine, of course, if you do carbon capture, you could carbon capture it and quickly process it into something useful. Another story from Professor Sankaran's lab, who has been a close collaborator of mine, as was mentioned earlier. He's reacted a nitrogen plasma with water and formed ammonia. So he takes N2 and H2O to get NH3. How does it work? That solvated electron reacts with a proton to form an hydrogen, and through what is conceived to be a series of chain reactions with the nitrogen forms ammonia. And it does it at very high yields, and as you'll see a little bit, at very high efficiency. So we know how to create things. The question is, how well do we create things? And in electrochemistry, we typically think of efficiency through the amount of charge that we're putting in versus the amount of product that we get. And so you want to look at the amount of product relative to the amount of charge. If we are just reacting it with, say, water to get ammonia, that's our product. That's what we want. But if it's electrolyzing water, that's a side reaction we don't want. And so that's going to reduce our efficiency from 100%. And we observed, both in our own experiments with Mohan on silver reduction and then in his own experiments with ammonia, that under certain conditions, certain times, certain concentrations, or certain currents, you could get 100% efficiency. And the question is why? Why can you get 100% efficiency? What is the driver of this? So we took these two reactions and we developed a theoretical model for this that said, if we're, in this case, we used chloroacetate rather than silver as our reactant. But if we have chloroacetate, we predict that the efficiency should scale linearly with the concentration of chloroacetate. So if we put more chloroacetate in it, our efficiency should go up. And that's this solid line that you see here. And then the data is what you see here on the bottom, which showed, wow, we were really, really wrong. That is not what's happening, okay? And in fact, we thought maybe one of the side reactions was with OH, which comes in from the gas phase. And so we added glycerol to try to scavenge that OH, and that did nothing. So those are these open circles here, right? But what we realized is that as we react away the chloroacetate at the interface, new chloroacetate has to come up from the rest of the solution. So it's a transport limited process. So if we include a transport limitation in our theory, it actually matches the data perfectly. And this is predictive. It's not only a curve fit. This is actually predictive, where we use only values that we look up from literature. Okay. To study this more, we actually created a computational model that again looks at the competition of these different reactions. And what we found is that we could get 100% efficiency, but only for a short amount of time under certain conditions. So that's what I'm showing here in this middle plot, 100% efficiency, and then over time it tails off, depending on what's happening. And it's because we figured out that the critical time constant scales with a few parameters. First of all, it scales linearly with the diffusivity of the scavenger, whatever you're reacting. Second, it scales quadratically with the concentration of the reactant in the bulk, and then it scales inversely quadratically with the current density itself. So if you want to affect the maximum amount of efficiency, right, you want that time scale to be really long. So you'd push your current density down or your bulk concentration down. or you want to pulse your plasma to be shorter than that time scale. And that's how you get 100% efficiency. Okay. Now, I've only been talking about chemistry. I realize most of you are like, there's a reason I'm not a chemical engineer. I hate chemistry. So I'll show you some cool physics. One of the things that happens is that as you increase the current of a plasma on a liquid surface, it starts to form really cool patterns. These are an example of a spot turning into a ring, turning into concentric rings, turning into other spots. What other people have shown is you get like flower-like patterns, all kinds of really cool stuff. The question is why? Why does the plasma like to self-organize like this? Well, we developed a theory that said, well, we can predict that the transition from a spot to a ring follows what's called a Turing process. So you guys might have heard of Alan Turing, the father of the modern computer. He's back in the day when scientists did everything, right? And so he also developed a theory about this type of pattern formation that you see all the time in nature. Why does a tree branch the way it does? Why does a river branch the way it does? And it basically is a conservation law that it wants to self-conserve. We see it in this, and it's driven by what's called an autocatalytic reaction, something that increases the amount of whatever you have faster than it can move. And so what increases the amount of something in a plasma? Ionization. It's an avalanche reaction. So it creates more and more electrons. So that is occurring faster than you can spread the electrons out. So then they want to form certain patterns to basically conserve energy, to minimize energy. Well, recently, others had shown that these plasma patterns dance. And so not only do they form these pretty spots or these pretty conditions, but they actually move in time. And so we decided to take a high-speed camera, and we noticed that there seemed to be 4 spots that formed between this ring and this big spotted pattern condition. We took a high-speed camera and we looked at it, and sure enough, please play. Hey, there we go. You see that the pattern starts to move and dance, and it sort of coalesces and decoalesces into spots. Very fast time scale, millisecond time scale. And we're like, why would that happen? Milliseconds is fast for a liquid, but it's actually really low for a plasma, right? The time scale for a plasma process is on the order of nanoseconds, not milliseconds. So that means there must be something happening in the liquid that's doing this. And we hypothesized that, and we could, well, first of all, we could extract a frequency from this, but we hypothesized that the driving mechanism of the frequency was actually the plasma forcing the liquid to oscillate and create these capillary waves. So the plasma pushes down, creates a force. There's a restoring force, right, from surface tension. The liquid wants to move, and you get these waves. And sure enough, when we looked really closely from the side, the plasma is right in the middle of this video. You can see all of these little waves, propagating out. And there's a theory for this, for these capillary waves, called a dispersion theory that relates their frequency to essentially the damping ratio, so the viscosity of the solution. And sure enough, our data across a wide variety of experiments all pretty much collapse exactly on this theory. So this is a really cool indication of how the gas phase and the liquid phase couple really explicitly in these systems. Okay, so that's plasma liquid. Very fast, I realize, but hopefully you saw some cool stuff. I want to talk about gas phase before I run out of time here. And this is called plasma catalysis. If you're not familiar with what a catalyst is or catalysis is, a catalyst accelerates a reaction without being consumed. So it's not one of the reactants. And so these are found in like your catalytic converter in your car. And the way they do that is by changing the energy pathways between the initial reactants and the products to lower the activation energy, typically. And so that's what you see here. And the question we ask is, what if we add plasma energy to that process? And really what that plasma does, we already know the plasma does its own chemistry. For all we know, in the absence of a catalyst, the plasma might take X plus Y and create Z. I've already shown you that to be the case. The question is, can we get a synergistic effect? If the plasma is doing it alone, Is it then coupling with the catalyst to do something where they're multiplying against each other? Or are they doing it independently? We just add them, right? So is there a synergy that occurs, or is this or is there some multiplicative effect? And that's the question we've been asked. And again, this is something we're not the first to study it. There's been a whole lot. I recommend you read this really nice paper that two of my collaborators contributed to. But again, we look at this from a variety of perspectives. One is you want to do catalytic experiments and do kinetic studies. Number two, you want to characterize the plasma. Three, you want to know the surface science. What's happening right at the catalyst surface? And four, can we do some computational modeling? Again, I've been collaborating with a lot of people on this. And I should have mentioned, you saw photos up in the upper right-hand corner of all the people I'm collaborating with. And I'll come back to that at the end. And you're going to see the same thing. Some photos of my collaborators. One of the things we built is this great reactor system. It's a dielectric barrier discharge reactor system. So it's a glass tube with an electrode down the middle, and then an electrode wrapped around the end. We run a high voltage AC frequency, we form a plasma. Inside that tube, right where the inner electrode is, we pack a catalyst bed consisting of microparticles with nanoparticles spread upon them. The microparticles are typically some sort of insulator, some sort of oxide like silica or alumina. And then the reactive catalytic material is a transition metal of some sort. We call this a transition metal supported, so an alumina supported catalyst. We can put this in a furnace to control the temperature. We can flow all kinds of reactants in and measure the products, and we can measure the plasma properties. So this is a really nice tool. We've actually built a couple of them so that we can do a wide variety of studies. This is an example, again, going to one of my use cases of methane plus carbon dioxide to form synthetic gas or dry methane reforming. And what you see in the top is the conversion of methane, which means that you're making a product with it. And we turn the plasma on and the plasma off. And the what you see is the closed dots is the conversion with the plasma on, open dots, plasma off. And what you see is that it's like a switch. You turn on the plasma, you get more. You turn it off and you get less, right? So there's clearly a combinatorial effect. What you see in the bottom is an equilibrium plot. If we adjust the catalyst to no plasma, that's the black curve. To run this reaction, you got to get up to about 600 degrees C, and then you see that you start to get some conversion. If we adjust the plasma with no catalyst, that's the red curve. At low temperature, the plasma does this chemistry by itself, but then at high temperature, it drops off. When you combine the two, that's the blue curve. What you see is that the blue curve starts with plasma alone, but then when the catalyst turns on, you get a synergistic effect where they actually get better than just the catalyst alone. And we know it's synergistic because the plasma itself does nothing at that temperature. Okay. We've also done this with nitrogen fixation or ammonia synthesis using nitrogen and hydrogen plasmas. And what you see is that there's a plasma contribution, but there's a catalytic contribution. I'm not going to go too much into the slide here, but what I want to point out in the bottom is that if I change the pressure of nitrogen, I get a linear relationship. And if I change the pressure of hydrogen, I get a flat relationship, which means that this process is controlled entirely by activating the nitrogen. Nitrogen, you need to get it from N2 to N to form NH3, and it's got a triple bond there. It doesn't want to break. So what can we do to break that triple bond? And our hypothesis is that the plasma activates that triple bond, making it easier to break. And we attacked that with this great computational modeling that I don't do, but my collaborator does, Bill Schneider, where he does density functional theory and microkinetic modeling to predict reaction rates across a variety of reactions. And we just build a whole network of first-order reactions or first-order differential equations, solve those in MATLAB or whatever your Python, whatever your favorite code is. And using density functional theory to get the reaction rate constants, we can actually predict some behaviors. So we go back to this ammonia synthesis, and we asked ourselves, what could the plasma be doing, right? If there's this strong dependence on nitrogen, so the first reaction is you have to take nitrogen, split it, if that's the rate limiting step, what could the plasma be doing? Well, we know the plasma is vibrationally exciting the electrons, the nitrogen, like I discussed earlier. And so that puts it into a higher energy level. So therefore, the apparent activation energy that is being observed, the energy barrier, is lower when you're actually excited in a vibrational state. We can predict that with this computational modeling because it changes the initial energy state, changes the activation barrier. And if you have a plasma off condition, this is the log of the turnover frequency, which is essentially the rate, as a function of the binding energy to N2 for different metals. You see that when the plasma is off, you have a peak right around ruthenium. That's your best catalyst for this. But if the plasma is on, our modeling predicts that because you've excited the nitrogen, it's now easier to associate. You actually move what's called the volcano curve to the right, such that, as the blue curve shows, your peak metal is actually cobalt. It's not ruthenium. And what I show you here in the plot adjacent to this is the evidence that cobalt is actually outperforming iron, ruthenium, nickel, and platinum. So this excitation by the plasma is one of the sources of synergy that you get with the catalyst. But more importantly, what it tells you is that you need to redesign the catalysts, use different metals when you're working in a plasma environment. Here's another really cool study we did, which we show, again, with ammonia synthesis, that we can get beyond equilibrium. And so the black curve, what you see there, is the ammonia yield as a function of temperature. That's equilibrium. That's the equilibrium curve. And if we add the plasma to it, the data that you see is that it goes beyond equilibrium, but then at some point, it starts to tail off. And if you actually look at the orange, which is nickel on alumina, that actually follows the equilibrium curve pretty well. And the question is, why was that happening? Well, the plasma can drive this ammonia synthesis beyond equilibrium, but at some point, the catalyst sees an equilibrium reaction and it drives the ammonia back to nitrogen and hydrogen. And nickel's a really good catalyst. So nickel was doing this better than platinum. And so the nickel wanted it to be at equilibrium because it was catalytically reversing the reaction rather than driving it forward. We've also been doing some interesting surface science using what we call polarization modulation, infrared spectroscopy, or infrared absorption spectroscopy, PM-IRAS. We created this nice little chamber. We bring in an infrared source that gets photo modulated so that you basically polarize it. You shine it on a surface and then you can detect it. We bring in a plasma jet to react on that surface with the metal of the surface of our choice. We can measure the gas phase with a residual gas analyzer, a mass spectrometer. We can measure the plasma phase with an optical emission spectrometer. So we have this really nice multimodal tool that we've developed in combination with Casey O'Brien. And the question that we were asking is, what is the role of the plasma in potentially reacting with stuff that's already on a surface? And so if we have methane and we put an argon plasma, the argon plasma is going to excite that methane, dissociate that methane, and then it's going to deposit stuff on the surface. This is how you grow carbon nanotubes or diamond or anything like that. And then a question we said, well, what does the argon do in this plasma by itself? So we turn the plasma off, we flush the system, we have all this carbon deposit on the surface, then we hit it with just a pure argon plasma and see what happens. And particularly what we want to know is whether we can form C-C bonds. We can go from carbon-hydrogen deposits, CHX deposits, to carbon-carbon coupling. This is part of the idea of then when we react with nitrogen, we get this great nitrogen-carbon coupling. And actually, we've done that, but I don't have time to talk about it today. But what I will show you is on the top surface, top plot, you have nickel. On the bottom plot, you have silicon dioxide, just as a reference. Nothing happens in silicon dioxide. It's pretty boring. But on nickel, you get these wonderful CH deposits, just like I described. Then we flush the system. We run just argon impinging on the surface. And sure enough, the argon pushes the CH on the surface to form these C-C bonds. Well, it does nothing on the silicon dioxide. So there's a nickel component to this, there's a catalytic component, and then there's this reactive component as well. We can monitor the products of this. And so not only do we get hydrogen as we expect, we get these higher order hydrocarbons that form from these C-C coupling, like ethylene and ethane and acetylene, form that from these C-C bonds. And so we're upcycling methane into more complex hydrocarbons. And again, if we then hit it with a nitrogen plasma, we can form some really cool nitrogen products, but that's not ready for prime time yet. The last part of this, which is more on the plasma side, is we wanted to know if the plasma is helping drive catalytic chemistry, is the catalyst itself doing anything to the plasma? Is exposing the plasma to a catalyst changing the plasma inherently in and of itself? So we just modified our DBD reactor a little bit, but we did some optical characterization and a wide variety of electrical characterization to get the capacitive, what we call the filamentary behavior. So what you see is individual plasma filaments, which are those spikes on the current graph, to show what's the relationship between those macroscopic measurements and the catalyst. So again, we went back to ammonia synthesis. You already know cobalt's the best catalyst. So I showed you this plot before. So we took 3 of these metals and we put them inside. Then we did all these plasma diagnostics on it and wanted them showing you just a single one. This is the time averaged filamentary current. So we look at all those individual filaments and we look at the average amount basically per filament. And what you see is it didn't matter what kind of catalytic material we used in our system. We could have added more metal or less metal, and it wasn't really changing that behavior. And everything if you read the paper, we've got like 6 different plots that basically look like this. So that the catalyst doesn't change the plasma. What we saw earlier from the on-off stuff is that the plasma is not irreversibly changing the catalyst. It's not changing it as a fundamental thing, because once you turn it off, you recover to the original state. So there's a synergistic effect. So all of this goes back to say, yes, plasma catalysis, there's synergy. You have to rethink how you design your catalysts for these non-equilibrium environments, and then you can potentially do some really useful and interesting chemistry. So those are my 2 stories for you today. I did it. I know I went pretty quickly at a high level, but hopefully you appreciated the potential of these technologies to electrify our goods production across the globe. And maybe if you get bored with whatever you're doing, you start working in this space and helping us advance the cause. I do want to make sure I thank the groups I worked with. On plasma electrochemistry, I've been working with Paul Rumbach, Dave Bartels, Chia Chang, Daniel Elg, who's a Ph.D. alum of this department, and Professor Sankaran, who's also a professor here, and a wide variety of students as well, including Daniel Martin that you see there in the glasses, an alum of this department as well. And then for plasma catalysis, I will work closely with Jason Hicks, Bill Schneider, and Casey O'Brien, and a wide variety of students as well. In particular, Kiram Lee, who's right here, is also an alum of UIUC. So keeping the connection strong. And with that, I'm happy to take any questions. Thank you.